Okay, so I think that the only video that I'm gonna make for chapter 3 is gonna be this video on the energy of a string. Just because I think the book, I don't want to say it leaves out stuff, but it does kind of leave out some things like the formula, like where the formula for potential energy comes from, and things like that. And I just want to say a little bit about it. So first of all, I want to discuss the potential energy in a string. So I don't have nearly enough room to tell where the potential energy comes from. So I'm going to do it over here. So imagine we have a piece of string. Okay, so let's first think about this. If I have this string, so I'm gonna have let's draw. I'm gonna have some. This is the string coming from infinity or minus infinity, and then the string is gonna look something like this, and it goes off into negative infinity. Okay, I want to zoom in maybe on just this part right here and see what's going on in just this part right here for a length of delta x. So this distance, that distance there, I'm saying delta x. So if I zoom in on that bit of string, this orange part is an approximation to that part right there. This distance here is delta x. Okay, and let's think about this distance here. Okay, so what is this distance going to be? This is going to be the corresponding change in u. So if I call this point here x1, comma u evaluated at x1, which I'm going to call u1 for ease of notation, and if this point I call u2 and then u evaluated, delta u is equal to u2 minus u1. Okay, we're about to do an approximation. There's two ways to do the approximation. I'm going to do the approximation. First, it's not going to be an approximation. It's going to be exact. And because of that, maybe I should be more precise here on what exactly I mean. So this is u2, u2 is u evaluated at x2 for some fixed value, and then u1 is u evaluated at x1 for that same fixed time. Okay, by the mean value theorem, there is some number, I will call it just, let's say a, where x1 is less than a is less than x2, and this is going to be the x derivative of u evaluated at a times the length between the distance between x1 and x2, which is delta x. Okay, so now I'm going to do this approximation. So we have this approximation in the string that there's only going to be small deviations. So what this means, one way to think about this is that the derivative is continuous, even differentiable. So this can be approximated as u of x1. So the derivative evaluated at x1. Another method for doing this approximation method number 2 is to Taylor expand u at the point, like the center, centered, I'll say centered at x1. That's a method 2, and you ignore the higher order terms. We're going to do that in just a moment, but you ignore the higher order terms. Okay. So I'm going to call this orange part here, this is going to be called, I'm going to call this L2. Okay, so why am I calling it L2? Well, I'm going to say that delta x is L1. Okay, so why am I saying that? So I'm going to think about the potential energy in a string as being like modeled by the potential energy in a spring. So if I have a spring and I stretch it, the potential energy is just equal to the force of my holding it times the distance that I've stretched it. Okay, so the potential energy V is going to be equal to delta L times the tension in the string. Okay, so what is delta L? Well, delta L is equal to L2 minus L1, times t. Well, this is just equal to L2 minus delta x times t. Okay, so let's look at the L2 minus delta x, or let's approximate delta L. So L is going to be equal to the following, just by the Pythagorean theorem, and using the just by the Pythagorean theorem, it's going to be delta x squared plus delta u squared. It's going to be the square root of that. That's what L2 is. Okay, really for any L, this is what it is. I mean, this is just the formula for L. If delta u is 0, if delta u is equal to 0, this just says L is equal to delta x, which is what we're thinking about. But for the diagram we have up here, L2, this is what L2 is equal to. This is what L2 is equal to. Okay, now we're going to use our approximation. So we're going to have delta x squared. Okay, but delta u is approximately going to be delta x times the x derivative of u. And just note that the x derivative of u is being evaluated at x1, but because it's the notation becomes too cumbersome, I'm not going to write it. Okay, now this is equal to delta x times the square root of 1 plus the u derivative of x squared. Okay, now I want some way to approximate this blue thing, the blue square root. And I'm going to say the following. Whoops. I'm going to consider the function f of, I'll say a will be my variable because I'm using x up there. So f of a is going to be equal to the square root of 1 plus a. And now I want to Taylor expand, really Maclaurin expand, at 0. And so I'm going to get f of a is equal to f of 0 plus f prime of 0 times a plus higher order terms. Okay, so f of 0 is equal to the square root of 1 plus 0, which is just 1. So f of 0 is just 1. F prime of 0, again, it's the derivative of f, a value. So if I take the derivative of this function and evaluate it when a is equal to 0, it's just going to be 1 over 2 times a, and then I'm going to get something, again, the higher order terms. And then so finally, this is approximately equal to 1 plus 1 over 2a. Okay, so now I want to apply, and you could have done that same approximation using the mean value theorem as well. So then up here, this is approximately equal to delta x. So now I'm plugging in a for the, so now this whole thing is going to be my a. So this is 1 plus 1 over 2 times the x derivative of u squared. Okay, so that's what L2 is. Okay, so then again, if I just want to compute delta L, that's going to be L2 minus delta x. So this is my approximation for L2. And if you come up, so let me continue my approximation for V down here. I have V is equal to L2 minus L1 times T. Okay, so this is equal to L2 minus delta x times T. Okay, and using my approximation, L2 is 1, is delta x, because so if I distribute the delta x, it's delta x plus delta x over 2 times the x derivative of u squared, and then I'm going to minus delta x time, and I get that. Okay, so all together then, the potential energy in this little segment of string is just equal to that right there. Okay, so then what this means, times the t. And so what this means is that the potential energy in the whole string is going to be the integral from minus infinity to positive infinity, t over 2, that's a constant, times the x derivative of u squared dx. Okay, so now let's think about the kinetic energy in a string. So kinetic energy, remember kinetic energy is equal to 1/2 mass times velocity squared. Okay, so this is a little bit easier to think about. So if I have a string, if I have a little segment of string like this, for that little segment of string, the mass is going to be the mass density, which is rho, times the length of the string, which is delta x, times its velocity squared, which is the t derivative squared. Okay, and then so this tells me that the kinetic energy on the whole string is going to be equal to the integral from minus infinity to positive infinity, 1/2 rho, the t derivative of u squared dx. Okay, now I want to point out an assumption that I haven't stated explicitly, but I want to use it now. I want to make two assumptions, or really just one assumption. I want to assume that the initial profile of the string is finite. So in other words, I want to assume that phi and psi are equal to 0 when x is bigger than some big number. R could be 25 million, but I'm just going to say that as you go off to infinity, the limit of both phi and psi as you go off to plus and minus infinity are going to be 0. So in other words, I'm saying the initial profile is going to be 0, 0, 0, then it might do something like this, and then it's going to be 0, 0, 0 as we go on in this direction and this direction. If it's not 0, then there's not going to be finite kinetic energy. And then there's always going to be infinite kinetic energy, so this stuff that we're about to talk about won't make sense. I mean, but these integrals will be negative is what I'm saying. The other thing that isn't really an assumption, but I just want you to remember, is that we can write the equation. So we can write it with the c squared, but this is equivalent to writing t second derivative like this is equal to rho times the second t derivative. Okay, that'll be important for just a moment. Okay, I'm also definitely going to need to insert another page here. Okay, I'm almost certain I'm going to need to use that. Okay, so now what I'm going to do, so the calculation that I'm about to do, I'm about to show that the derivative of kinetic energy in this string with respect to time is equal to minus the derivative of potential energy with respect to time. So this means that the derivative of energy, the time derivative of energy, is going to be equal to, well, this is equal to the derivative of kinetic energy plus the derivative of potential energy. Okay, because there's only two kinds of energy here. There's kinetic and potential energy. But this equation here tells me that the kinetic energy derivative plus the potential energy derivative is equal to 0. So in other words, this is going to tell me that the total energy is conserved in this string, which we should expect. Okay, but now we're going to show, like, from the equation that the string conserves energy. So this is just kind of using the math. We're showing that math-wise, the string is going to conserve energy. In fact, we could just take this. There's a sense in which we can take this as the definition. Like, we're just defining this thing called potential energy, and this is what it's equal to. And over here, we're defining something. We're just defining this thing called kinetic energy, and this is what it's equal to. And then down here, we're defining this thing called total energy, and we're just saying that energy is equal to the kinetic energy plus the potential energy. And to do the very mathy thing that we're about to do, that's all that we need to assume. Okay, but physically, I'm saying that, physically there's this nice physical interpretation as well. Okay, and motivation as well. All right, so let's just compute this. Let's compute the derivative of kinetic energy with respect to time. So we're going to have, let's see, what's a good color for this? Let's do purple. The derivative of kinetic energy with respect to time. Well, this is going to be equal to d dt. I'm just going to write my formula for kinetic energy. Well, let's come back up here. This is going to be rho over 2. This is rho over 2 times the integral from minus infinity to positive infinity of the t derivative squared dx. Okay, so now I'm going to take my derivative and put it on the inside. I'm going to have rho over 2 on the outside for now. When I take the derivative and put it on the inside, I have to use the chain rule, and when I do that, I'm going to get 2 times the t derivative of u times the double t derivative of u dx. Okay, so the 2 and the 1/2 are going to cancel. Now I'm going to use the fact that this satisfies a differential equation. So rho times the double t derivative is equal to t times the double x derivative. Okay, so this is going to be equal to t times the integral minus infinity to positive infinity, the t derivative, and then the double x derivative of u dx. And there's a u, whoops. There's a u that goes here. Okay, so now let me pause for a moment and remind you of integration by parts. Integration by parts says the following. It says that if I'm looking at the integral, let's say from minus r to r, of f of x times g prime of x, okay, whoops, dx, this is equal to f of x g of x, and we're going to do the evaluate this from minus r to r, minus the integral from minus r to r f prime of x g of x dx. Okay, well, let's assume that f and g both have compact support, meaning for some value of r is going to be 0 after r and 0 minus r. So in other words, assume, well, I want to assume, let me not write that. So I want to assume that f and g are both 0 outside of some big interval. So assume f of x is equal to 0, g of x is equal to 0 for large enough x. Similar to how we're thinking about phi and psi. Okay, well, so if that's true, it means those terms are going to be equal to 0, because if r is big enough, because if r is big enough, it means those terms are going to be equal to 0. And so then this is just equal to minus the integral from minus r to r f prime of x g of x dx. Okay, so let's continue that. Let's use this idea to continue with our computation up here. So purple means I'm continuing from up there. So this, I'll call this star. So now I'm saying, what is star equal to? Okay, well, I'm going to say, notice this is the double x derivative. I'm going to call this is going to be my g prime, and this is going to be my f. And so using my integration by parts idea, this is going to be the t derivative of u times g. So g prime is the double x derivative of u. So this just means g is going to be the x derivative of u. And we're going to evaluate this from minus r to r. Okay, actually, let me back up a step here. remember, so I'm going to be a little careless with how I'm defining the improper integral, but this is equal to the limit as r goes to infinity, t minus r to r, the t derivative of u times the x derivative of u dx. Okay, and again, I'll just rewrite what I had above. I'm saying this is going to be my f, and this is going to be my g prime. So now this is equal to the limit as r goes to infinity, t, I'll have this t on the outside, it'll be f times g, so it's going to be the partial derivative of u with respect to t. So if g prime is the double x derivative, this just means that g is going to be the single x derivative, and we're evaluating this from minus r to r, and then it's going to be minus the integral from minus r to r. So now I'm going to put the derivative onto f, which in this case means I'm going to put the partial derivative onto my f. So this is going to become the mixed partial derivative, partial x, partial tu, times partial x u dx. Okay, so now observation. U and psi have compact support. Okay, this idea about finite propagation speed that was covered on the previous page of notes that I didn't make a video on, but you can read about. The observation, this is phi and psi, have compact support. Okay, the finite propagation speed means that at any time, u will have compact support. So for any finite time, u is going to have compact support. So this is a fundamental idea about this equation. It's an example of something called a hyperbolic equation, and one behavior that it exhibits is this finite propagation speed. So u has compact support. Okay, so what does that mean? It means that for large enough values of r, this is equal to 0. For large enough values of r, that's equal to 0. Okay, and then so this is going to be equal to minus t, and then it's going to be the limit as r goes to infinity of this integral there, but that's just the same as this improper integral. You know, essentially by definition, you have something like this. Okay, so now we're going to kind of make this inspired guess here. So if I look at this right here, this looks like something that we might have gotten when doing the product rule, or sorry, the chain rule with the t derivative. Okay, in particular, this is equal to minus t times the integral from minus infinity to positive infinity. So I'm going to have here the x derivative of u squared, and on the outside, I'm going to take the t derivative. Okay, now, and I'm going to have to divide this by 2. Okay, so just take the t derivative, just actually compute this, and you will see that it's equal to that, just by using the chain rule. And then dx. Okay, but now this is equal to minus d dt. I'm going to factor that 2 out, t over 2 times the integral minus infinity to positive infinity, the x derivative of u squared dx. But this part is just kinetic energy, or potential energy. So this is minus the derivative with respect to t of kinetic energy. Okay, so I've got minus the derivative with respect to t of kinetic energy all the way down there, and all the way up here, I have the derivative, I said kinetic energy, I said potential energy, but I wrote kinetic energy. Okay, so this is minus the derivative of potential energy, and up here, this is the derivative of kinetic energy. In other words, the derivative of kinetic energy is equal to minus the derivative of potential energy, which is exactly what I said I would prove there. Okay, So finally, I want to use this. So again, we're using terms like energy, potential energy, and kinetic energy because they are motivated by physical concepts. But we could just define them as mathematical concepts and forget about the physical concepts. And that'll make the next thing that we're doing true even without the physical concepts. Now, I'm not saying it's good to forget about the physical concepts. Don't hear that. But I'm just saying there's all these approximations going on when we say the potential energy is this, the kinetic energy is that. But I want to prove a very precise mathematical statement that doesn't rely on energy things. Okay, so in other words, let's just back up. Let's abstract for a little bit. We have this thing in orange that we're calling kinetic energy. We have this thing in purple that we're calling, we have this thing in orange that we're calling potential energy. We have this thing in purple that we're calling kinetic energy. And we know that the total energy is the sum of those, and the total energy is conserved. So the energy in the string is going to be the energy in the string for all time. And I want to use this to prove the following theorem. So assume phi and psi are compactly supported continuous functions. That's not completely necessary, but I just want to say it. And that u1 and u2 satisfy the initial value problem. Rho, so this is just the wave equation written in this form. U of x0 is equal to phi of x, and the t derivative of u equals psi of x. Okay, so I'm saying u1 and u2 both satisfy this equation. Then the conclusion, so that's the hypothesis of the theorem, the conclusion is that u1 is equal to u2. So in other words, we've already seen that there are solutions. We kind of, in the first three sections, those kind of explained, though maybe you weren't convinced that that's the only solution. But now we're going to give kind of a very watertight, airtight, whatever proof that if you have two solutions to this initial value problem, then they're equal to each other. So we have a uniqueness theorem. We've already done the existence theorem. The D'Alembert solution gave us what the solution is explicitly. Now I'm going to show that's the only one. And notice that's different. That's much different than when we are looking at the first order quasi-linear equations and things like that. Okay. So proof. Okay, so essentially what we're going to do, well, let me just back up. So let W equals U1 minus U2. Okay, well, W equals U1 minus U2. We're going to show, our plan is to show that W of xt is equal to 0 for all values of x and all values of t. That would mean that U1 is equal to U2. So how are we going to do that? Well, notice that if U1 and U2 both solve this orange equation, then W is going to solve the following equation. It's still going to satisfy the PDE. Okay, this is a linear PDE, so W is going to satisfy this. But what is W of x0 going to equal to? Well, this is just going to be U1 minus U2, but U1 is equal to phi of x and U2 is phi of x, so this is 0. Okay, and similarly, the t derivative of W is going to be equal to 0. Okay, so what is the energy in the string at time 0 for W? I'm going to put down here W, meaning the energy at time 0 for W. Well, the energy at time t for W is going to be the sum of the potential energy and the kinetic energy. So the potential energy is going to be t over 2, the integral from minus infinity to infinity. It's going to be the x derivative of W squared plus, actually I just want to write this as one integral. Let me be a little more precise here. So this is going to be t over 2 times t over 2 times the x derivative of w, like this, that whole thing squared, plus rho over 2 times the t derivative of w, that whole thing squared dx. Okay, well, if t is equal to 0, I know that this whole thing is equal to 0. Why do I know that? I know that w of x0 is equal to 0. I know that wt of x0 is equal to 0. So this is equal to 0. Okay, so in other words, by this conservation of energy, this should be true. It should be equal to 0 at any time. And so this is going to be the integral from minus infinity to positive infinity, t over 2 times the x derivative of w, like this, okay, so notice that this integrand is greater than or equal to 0 because we're squaring it and because t and rho are positive. So the conclusion, the integrand itself must be equal to 0. The integrand itself has to be identically equal to 0. If you're integrating a non-negative function and it's equal, and the integral is equal to 0, then that function has to be equal to 0. So if the function itself is equal to 0, okay, so then both non-negative parts of it have to be equal to 0 as well. So the conclusion then is that the x derivative, this is identically equal to 0 for all values of x and all values of t, and the t derivative of w is equal to 0 for all values of x and all values of t. Well, if I have a function and the partial derivatives are all equal to 0, that means w of xt, well, this is just going to be w of x0, because if it's not changing with time, it means just going to be whatever it is. It's just going to be whatever it is. If I have a function w of xt and it doesn't change with time, if I fix an x and that's not changing with time, then w of xt is just going to be w of x, w of x0. It's not going to change. Well, w of x0 is just equal to phi of x. So there we have it. Okay, so this tells us now, and phi of x, for this problem, I'm kind of overloading the term phi of x. So I know for this problem, w of x0 is equal to 0. And so that's equal to 0. Okay, so in other words, this tells us that w of x is equal, this tells us that w of xt is equal to 0 for all values of x and all values of t, all values of x and all values of t. Therefore, the function itself is equal to 0. Therefore, u1 minus u2 is equal to 0. Therefore, u1 is equal to u2. All right, that's it for this video. I know it was kind of long.